Yeah, so welcome back, guys. And literally, we're looking at the calculation of oxidation numbers. I'm just taking 3 examples because it is simple, and I've done an example here, and even here, that's what I did there. But I want us to be more clear on it. So, calculation of oxidation numbers. Now, when you calculate oxidation number, you will actually pick an element whose oxidation number you have to find in your exam you will be given. So in this question, let me underline the ones I So the elements I underlined in the compound are the ones that I want to look for their oxidation number. And this one, I want to be really quick because you guys be smart, like you have to be smart. It's not let the oxidation number be X, blah blah blah. You can't do those ones in the exam. The exam is 2 hours, you are timed. You don't have the luxury of time. So you have to be smart. Just know that anyone looking for by default is only X. Since you're looking for this, you have to find X. But so let's just dive into it. So H3PO4. This is tetraorthophosphate 5 acid. So there are ways you can name this thing actually. I know you'll be like, maybe I name it for real. I didn't even know his name, like I crammed the name. I just like name it and okay, yeah. And you will see why that is. So let's know the oxidation number of phosphorus here. So normally nitrogen is X. So let's do the oxidation number of hydrogen is what? Is 1. So 1 times 3 is what? 3. And please note, since this compound is neutral, it has no charge on it, so everything will be equal to what? 0. I've said this before. So the oxidation number of hydrogen is what? 1. 1 times 3 is what? 3. Plus phosphorus, we will call it what? X. And it has no number attached to it. Plus oxygen. What is the oxidation number of oxygen? This is -2. So that is plus 2 brackets plus -2, and there's 4 atoms of oxygen. -2 times 4. Do you understand? And now equals everything equal to 0. If I say input hydrogen equal to 1, this is the oxidation number of oxygen equal to what? -2. So I don't know what I'm doing. So when we add everything here, we also do a normal collection of like things and we get our X. So anything we get as X, we give us the oxidation number of what? Phosphorus here. So that means 3 plus X. -2 times 4, -8. Minus times plus -8 equals to 0. That means X equal to 8 minus 3. Therefore, X equal to 5. You can put then the oxidation number of phosphorus, right? Let's see. H3PO4 is plus 5. This is sign here. Because it's a -5. You have that there. We'll do the same thing for this one. Here we're looking for chromium. You get this the one of the oxidation of chromium in this compound. And this compound has a charge assigned to it. That is, this compound is not a neutral compound. So what do we do? Let chromium be X. So we have 2 atoms of chromium here. That will be 2X. You get, we call chromium X, 2X plus oxygen here to be what? -2. Because this is not a peroxide, this is not a superoxide. You get plus -2. Need to call 7 times. Times 7 equals to what? -2. So that will be 2X plus 7, that will be -14. -14 equals to -2. Let me clean this. That will be 2x equals to -2 plus 14. 2x equals to 12. Then you have to sign by 2 to get x. So x is equal to 6 plus 6 is. So the oxidation number of chromium in this compound is what? 6. And the third one that I wrote before I took it was chlorine. Now, remember I said that an element in the uncombined state, or an element that combines with itself to form a molecule, the oxidation number is what? 0. Very simple. So, to make that all these things I said sticks into your brain, please, I beg of you, your personal study is very crucial to your academic development. Go and look for questions to solve. Don't assume you know them. Solve some questions, maybe 1, 2, or 10, and be sure that you know this concept. Now I'm moving on. Now that I've gotten the knowledge on oxidation numbers, this knowledge that we have on oxidation numbers can help us in the naming of most inorganic compounds. It can help us in the derivation of their molecular formula, and even the derivation of their IUPAC names, like how you see that I named this one tetra-orthophosphate 5-acid. I'll tell you. Now, the reason why we can apply the knowledge of oxidation number in naming of inorganic compounds and even writing their formula is because of something called combining powers, or we call it valency. So let's look at combining powers and valency. So while looking at combining power and valency, and as I was saying earlier, the knowledge that you got from oxidation number will be helpful if you are naming inorganic compounds or doing their formation. Now it is that most of these inorganic compounds, they are formed due to the exchange of combining powers. You get? And since you are seeing those reactions, most of this exchange of combining powers are due to the gain or the loss of electron, and that is like the building foundation of what reduction and oxidation literally means. So what do I mean? Now, there is a relationship between combining power. Please, I would like to use word valency. This one is too long. I don't like stress. So the relationship between what? Valency and oxidation number. Now, for example, for this sodium ion, if I ask you that what is the oxidation number, the answer is what? 1. Please. That's why when I was doing some calculations here, I made sure, or even if I didn't, it was a mistake, make sure that when you calculate oxidation number, you put the sign. That's where jam can hook you. Just do it fast and they will put, let's say the answer is 6, you can put 6 plus 6 minus 6. And if you are rushing, you are fast, you are good, and you are shining in pieces, you fail intelligently. Here you get, and it's not happening to you. So the oxidation number of sodium here is what? Plus 1. But we are looking at the valency. Valency is 1. The valency of this sodium ion is 1. Valency is the same thing as oxidation number, but you will ignore the what? The sign, whether positive or negative. So the valency of sodium is what? So this number is oxidation number. Let's write more code. Number. This also has this oxidation number, and this is valency combining power. The valency of sodium ion is plus 1. Why the valency is what? It's just 1. Why for oxygen? I don't know, it's what? Plus 2. Why the valency is what? 2. Or combining power. Okay, good. So when elements want to combine, there will be exchange in these combining powers. And when they exchange combining powers, it will also influence their naming. Let's look at a simple compound. For hydrogen, for H2O, this is water, H2O. Now, we all know that let me talk about this. For hydrogen, so hydrogen ion, the oxidation number is what? 1 plus 1. And the combining power is what? 1. Let's look at the compound now, H2O. Now, the reason why this formula is like this is not because we decided that it should be like this. It's because there's an exchange in combining powers. Or valency, this combined powers. I don't want to. As a vibe comes, I can send you what I want to say. So, the reason why this H2O is like this is because of the actually most combining powers. Now, okay, that's what I want to say. The combining power of hydrogen and oxygen is 1 and 2. This is and this. It is 1, let me put one like this so you can understand. It is 1 and 2 respectively. That is our combining power. Now, what happens is that there is an exchange due to the gain and the loss of electrons, which I will later explain when we now really start the meaning of reduction and oxidation in different terms. So, what happens, I'll just run you through this briefly, is that there's exchange. So, let's say hydrogen and oxygen to combine. What is the combining power of them? This is 1 and this is 2. What now happens at that? There will be an exchange. Do you understand? So they will exchange combining power. So 2 will come here, 1 will come here. That's why we write this as what? H2O. So it will be like, why does it put 1? Doesn't really matter because it's just 1 that is there. But assuming this was 2, you can put 2 here. 2 you get. Very simple. Very, very simple. Now, this will now influence the naming. We call it what? H2O. Or we can call it dihydrogen oxide. It's not really, you can call it that, but we want common names like what people can relate with. So if I say dihydrogen oxide, it will take you a while to realize that it's what I'm talking about. Do you understand? But so call it H2O. So later on we'll look at compounds that we apply these things to. We'll form the compounds, and I'll show you how you can name them easily, at least the most common ones. Now it means that we have many elements, we have many ions, and as oxidation number of some elements varies. For example, what's my this thing? Don't worry. For example, something like this. No, I told you earlier that we have CO, we have CO2. You get it? So, as the oxidation number of carbon in carbon monoxide, or we can call it carbon 2 oxide, or let me use the normal terms. As the oxidation number in carbon 2 oxide and carbon 4 oxide is different, so also their valency is different. So the oxidation number of carbon here is what? Is +2. While for here is what? +4. That means their combining power is what? 2 in this carbon 2 oxide and 4 in carbon 4 oxide. And that is why we need this carbon 2 oxide, showing that the combining power of carbon here is what? 2, and the oxidation number is what? +2. Same thing goes to this one. Now, I think that the combining power or valency of elements and of ions and compounds varies. It depends. Now, if I'm writing elements that their combining power is 2, I can put carbon there. And if I'm writing for those that their combining power is 4, I can put carbon there because carbon fits in the 2 occasions. Same as nitrogen. I can put nitrogen under elements that have a combining power of 2. I can put nitrogen under elements that have a combining power of 5, have a combining power of 3, have a combining power of even 4. Because in NO2, the combining power of nitrogen here is what? It's 4. Do you understand what I'm saying? And I go anyway. I also put the oxidation number of nitrogen here. I will get the combining power of nitrogen. Very simple. So I would have loved to write various elements. Of course, I will do the common ones that I can remember offhand. But there are so many and they are so fast. But there are some ones that I will have to know, and I will try to remember all. And if I can't, maybe I will bring a book and write it down. Or when I'm editing this video, I'll just display it on one side of the screen so I can see it. Or Better still, you can do your own research and just check it using a textbook or on the internet. So I'll show you that oxidation number is very, very crucial in combining one valency and in naming inorganic compounds. And even during their formation, it is very, very much involved. I could have gone into where I will do their formation now, where you can see it, but you need to know the combining power of some ions. Like for example now, CO2 minus. The valency is what? 3. NO3 minus. This is 1. OH minus is 1 for SO4 minus is 2. So these are the common ones, although there are very many other ones. So let's start the information of some compounds and let's go into how you can name them. Action. Wow. Welcome back. So in order to explain the naming and even the formation of some ionic compounds, I had to take it upon me to write these things down. And trust me, I'm a cohesive man. But really stressful because at the first instance, I was be like, guys, go and check it out. But I know some people don't check it out. And I think it's a little bit more better this way. So I also wrote the combining power of some common elements and some common ions. I even told you about myself to like write the names. You are welcome. So let's look at this now. I wrote this first column is the combining power. Combining power of 1, 2, 3, 4, and 5. And these are the elements that have those combining powers. For example now, elements that have the combining power of 1, hydrogen. The alkaline metals, the group 1 elements. Check this. Hydrogen, the alkaline metals, the group 1 elements, they have what? The combining power of 1. And even the halogens, they have what? The combining power of what? Of 1. Copper 1. Now, copper, they put what? 1 inside brackets. Or me, sorry, let me put them. I put what? 1 inside brackets. It means that copper has combining power of what? Of 1. Copper 1. Also silver has the combining power of 1. This should be thallium has the combining power of 1. And nitrogen can also have the combining power of what? Of 1. You get? So let's talk about what? Alkaline earth metals. That's the 2 element. I said it earlier. So they have the combining power of 2. Oxygen has the combining power of 2. Sulfur has the combining power of what? 2. Selenium has the combining power of what? 2. Also copper 2. They put 2 here, showing that the combining power of copper is 2. Iron 2, carbon 2, lead 2, nitrogen 2, and this thing 2. So group 3 elements have the combining power of 3, nitrogen 3, lead 3, iron 3, chromium 3, and everything. Same thing as carbon here, silicon, germanium, tin, lead, nitrogen. They can also have the combining power of what? Of 4. You can see that carbon is here and carbon 2 is here. Yeah. And lead 2 is here, lead 2 is here. Nitrogen is here, and here. So nitrogen can have my power of 1, 2, 3, 4. So we also note it, and when we are looking at the particle aspect, we'll be picking from there because we're combining different elements together. Same thing as ions here. So what are ions? Ions are a group of atoms that carries a charge. So this is the ammonium ion, NH4+. The ammonium ion, I'm not telling the name is ammonium. There's no any way you can derive it, like the Latin name kind of. So the name was ammonium ion, and that's the combining power of 1 because that's the charge is carrying here. So this is the oxidation number of 1. The combining power, that was 1. Then we have the nitrate 5 ion. Now, one thing to know is that when you are looking at things with elements, there's a way that you can derive the oxidation number of an element here. For example, Nigeria triiodonitrate 5 ion. This thing that the oxidation number of nitrogen here is 5. And we can do it. That was doing that real quick. I didn't even plan this. NO3 minus. So that would be, let's call it X. X plus oxygen is minus 2. Minus 2 times 3. X equals what? Minus 1. That would be x 392 minus 6 minus 6 equal to what? Minus 1. Then x equal to minus 1 plus 6. So x equal to what? 5 plus 5. So the oxygen number of nitrogen here is what? Plus 5. So you get. And the valency is what? 5. For nitrogen, not the whole compound. So, for example, now most of us know this compound. Tetraoxosulfate 6 acid. That is telling you that the oxygen number of sulfur is 6. So you get tetraoxosulfate 6. That 6 comes after sulfate. It's not like a trick, and you have to like me very well so that you don't stress your brain too much. And the same thing for dioxonitrate 3 ion. That is telling you that the oxygen number of nitrogen, because this 3 follows this, is after this nitrate. The oxygen number of nitrogen here is what? 3. You get, so if you see names like that we have this kind of structure, is just saying that it's like that. So the combined power of the dionitrate 3 ion, everything is 1, 4. This OH is called hydrogen ion, is 1, 2. This is tetraoxomanganate 7 ion. Now, what is the oxygen number of manganese here? You guess right, 7. Very simple. But the combined power of the MnO4 minus is what? 1. This one, so it's most times I will not be calling the IOPAC thing because it's stressful. Can I say OH minus, NO2 minus, NO3 minus? You know what it is, but calling the name is like stress. I don't like stress. So this is tetraoxochromate 6 ion. The original number of chromate here is what? 6. But the combining power of the ion here, which is CrO4 2 minus, together is what? 2. Everything like that. Like that, like this. I don't want to go through it. And you can see the IOPAC names. Yeah. And I'll teach you how to name all these things later on. So the thing is that when any of these ions or the elements, if they want to combine with each other, they will have to exchange their combining powers. For example, let me clean this place. I can clean this now. That's shown for you. Like we use box. No mind the box. So now, if any of these elements want to be combined together, they have to what? Exchange valency. Now, if I want to combine, for instance, I want to combine the ammonium ion and this together, I can combine it. So you get. Let's try. Now, what you first do, because I'm just introducing to you now, what you first do is that you write the ion or the element at the case will be first. Write it. And now want to combine NH form. Write it NH4 plus and SO4 2 minus. So now, next thing you write is their what? Is their valency. What is the this one? 1. This one, 2. Now, next is that they will swap it, they will exchange it. Change it. That will be 2 now come here, 1 now come here. So now, if you want to write the chemical formula of this, or the combination of these 2 ions, this is how we do it. Now put NH4 2. And please, you put a bracket here because this 2 is for everything here. Please note that. Then SO4. Yes. You cannot put SO4 1. No, not really matter. So this is NH42, then SO4. You've already combined these 2 together. Very simple as that. And that's how most of your inorganic compounds, ionic compounds, that's how they are formed. And you want to name this thing, you can name it ammonium tetraoxosulfate 6, because the original number of sulfur here is still 6, and you can check it out. So you get you can call this ammonium tetraoxosulfate 6. You can say ammonium tetraoxosulfate. You get. or you can put diammonium or because people know that for ammonium to combine with this sulfate ion, tetrasulfate 6 ion, of course it has to be 2 to 1. So you get. So now we've already written the chemical formula of this one. We can do for another one. We can do for another one. Let's do for now. I will carry an element and an ion. I just do ion to ion. Okay. Let me carry potassium and this one. Carry Cr2O7. What is the combined power of potassium? Just 1. It's a group 1 element. Plus. I don't put plus 1. So what we do now, we write their combining powers first. We are getting it. 1, this one is not 2. What do we do? Now exchange them. You get, we can what? 2 is not what? 1. Then add write it. Now put what? K2 Cr2O7. So use the formula now. Potassium potassium heptadichromate 6 ion. We understand. It's very simple. The reason why I know put brackets here, as you may want to ask me, is because it does not really matter. It's not needed because it's only one element that is here. But I think also, it's only one atom that is here. As if we have like more than one atom, I could have put the brackets. So together, okay, these two is representing every atom in that side. Do you understand? And let me do for one more. It's very simple. Let's do for a very common compound, which is KMnO4. The same is good for KMnO4. Let's say this is the same potassium K plus MnO4. From here, what is the combined power to? Is 1, MnO4 minus. So just say combined power is the valency is 1 here. So when you swap, it should be 1. So what I write K M N O 4. So no need for adding anyone because that was like 1. You can put K1 MnO4 1. It not really makes sense. Do you understand that? Very simple. Let's do for that one, and this should be the last one. It should be the last one. We can do sodium and let's pick this one CO2 minus. So 1, 2, swap, Na2, C3. Very simple. Sodium trioxocarbonate. Sodium trioxocarbonate. You can try for many things. And don't think that it's only this one, it's only all this one that have +1. I can actually take any one from here. I can take iron. I can take iron 2. I can take iron 3. For example, I want to take iron 2. Fe2 plus iron 2. And maybe chlorine, Cl minus. Goes 2, 1. Swap. 2 and number 1, 2. Now they now have FeCl2. As simple as that. Do you understand? So please, it's not restricted. You can actually take any one here and play with it. Depending on you play with it. You can combine this one and this one to give you sodium hydroxide. You know, if this one, this OH, let me do it here. Na plus and OH minus. You did it with 1, swap, no difference, 1, put NaOH. So you can see how all these things are formed. Now, I would like to touch something that someone particularly requested for me to do. And he or she said they don't really understand how to name all these compounds. For example, why is it sodium trioxocarbonate 4? Like, how do we know? And that is what we're treating next. Yeah, so guys, I'll be talking briefly on naming of some inorganic compounds. Of course, there is no fixed rule, but there are some arbitrary rules. So you get no fixed rule, but there are some arbitrary rules that have been noticed. Now, let's do that. I won't start stating the rules. It's through examples to get to know all these things. Now let's take a compound like Na2CO3 Kn. Let me give this KNN4. Let's put on K2CR2O7. Let's use these 3 compounds as a case study. Now, one thing you can notice is that all these compounds, they have a metal. If you are familiar with the periodic table and if you have some basic chemistry knowledge, you know that sodium here is a metal, potassium here is a metal, and potassium here too is also what? A metal. Now, when I want to name these elements, you name the metal first. Now, let's name this one. Let me use as a case study. If you want to name these elements, I will name this metal first. So I want to now have the word sodium. Do you understand? Sodium. Then I will now, after naming this metal, after calling the name of this metal, I will now start naming from backwards. I will start naming from backwards. And once you know that 2 is di, 3 is tri, 4 is tetra. The prefix and the suffix English. 5 should be like penta. 6 is hexa. 7 should be hecta. 8, which I feel you may not see, should be octa. Then 9 should be nona. Yeah. In chemistry, if you want to use this, you can say sodium 3 oxygen carbon. Does it make sense? That's how the back is. So if it's for 2, we call it di, 3 tri. So let me carry this in backward. I want to take this, you can copy it or note it. This ethanol pelta. So this is what I will name the metal first. Sodium. Then 3 is here. I will say what? Tri. Oxygen is what? Oxo. Carbon is what? Carbonate. It's not complete. Now, this is where your knowledge of oxidation number comes. Now, you may not know the oxidation number of carbon. This is why I can name it now without really doing any calculation, because I know it already. And you also know it, or you do know it already. This is sodium triorthocarbonate. 4 will be here. 4. Showing that the oxidation number of what? Of carbon here is what? Is 4. And maybe you've already named it to this extent and you don't know what should be here. Maybe it is 4, 5, or 3, because it's not in all cases that carbon will be 4 in all the compounds. Do you get? You can just read in a quick and rough work, just calculate for the oxidation number of what? Of carbon, and you get it, you put it there. Sodium triorthocarbonate. 4. Very simple. When you are calling oxygen, you use oxo. For carbon, you use carbonate. For nitrogen, you use nitrates. For which one again? For magnesium, you use manganate. For chromium, you use chromate. So you get adding 8 to some ones. For oxygen, you use oxo, not oxide. Which one again? For sulfur, you use sulfate. Which one again? Let me look. For phosphorus, you use what? Phosphate. For that's the one. That's the most common ones I possibly encounter. Now let's apply the same thing that we did here. Let's apply it here. What does it you do? The metal first. Potassium. This is metal, potassium. Potassium. What? Tetra. 4 is tetra. Tetra. This oxygen here. Also. Then we have manganese. You know, I think manganese is manganese. Potassium tetraoxo manganate 7. How did I get the 7? I calculated the oxidation number of what? Magnesium here, because that's where the naming is stopped. So you name the metal first, then you go backward and stop to the element that you don't need. Very, very simple. Let's do for this one. It starts with the metal, we name it first. So ignore the numbers here. Now we're not saying disodium could really make, like, it don't really make sense. And they don't do it that way. So for this one, they say what? Potassium. What? This 7 hepta-oxo. These two we take into consideration. Potassium hepta-oxo di. 2 is di. Chromium is now what? Chromate. What? 6. Now, I want to make a common compound. You know, like there's no way you do chemistry and you know encounter this compound like 5 billion times. So that now, from this naming, you know what tetraoxosulfate 6 acid. Tell you that the original number of sulfur is what? Is 6. Do you understand? So let me also do for one. Now, why don't I the original number of why do I not okay? Because I don't tetraoxo manganate 7. How do I not do 7? Very simple. Let's do for this one. KNNO4. I've told you before, this compound is neutral, there's no charge. So what the original number of potassium is a group 1 element is what? 1. 1 plus 1 for magnesium, let's call magnesium X. Plus oxygen is equal to -2. That means -2 times 4. Everything equal to what? 0. Do you understand? So that means 1 plus X minus 2 times 4 minus 8 equal to 0. So that means X equal to what? That would be 8 then minus 1. Then X is equal to what? 7. Think that the oxidation number of manganese here is what? 7. Do you understand? Please, do you understand? I didn't understand. So that will call it potassium tetraoxomanganate 7. Same thing happened for this one. Same thing happened for this one. Now let me touch another case study. I know when I was naming this one, you'd be like, sir, why did you say hydrogen tetraoxosulfate 6? And I need to know mind. So as I said earlier, the rules are not fixed, but there's some normal ones you should know. Like when you see a compound involving a metal. Like for instance now, let's say it's so now NaOH. This is also like sodium hydroxide. Name sodium first. There's no number here. You get? So just sodium. Then what do you call this ion? It's hydroxide. So sodium hydroxide. Same thing as this one. NaCl. Sodium chloride. NaBr. Sodium bromide. All these ones that they have just like two atoms in their molecule, and there's no number kind of there. You just name them normally. Even this one says HCl. Although this one is an acid, hydrogen chloride. I think I can clean this now. You can pause the video and look at it again. Whew. Now, in naming of compounds that let's say, should I say acid? Let's say acidic compounds. For example, HNO3, H2SO4. Which other carbon acid can I remember? Let's just use this two. These two is okay. The other acids are the HCl, HBr. Yeah. These are the two common acids I can really remember. Remember anyone in the way. Okay, H3PO4. Which is exactly part of it. So you want to name this acid. Most times that when you're naming acid, you don't consider the hydrogen, because we know that you saying that acid is like telling us that hydrogen is there. Do you get? That is an hydrogen ion there, because what's an acid? An acid is an the compound that when it dissolves in water, it produces hydrogen ion as its only positive ion. So if you know what an acid is, now for sure, there will be an hydrogen ion present. So we want to name acid, we don't really consider the hydrogen because literally hydrogen is not in metal. So we can't name hydrogen first, we just put it from here. Then we'll call this, then we start from here immediately. That will be tri-oxo, and this nitrogen nitrate 5 acid. You get, and we'll put the acid there because we have nitrate 5. So you don't put nitrate 5. Is it an ion or is it the acid that has hydrogen? Do you understand? So same thing goes for this one too. Let me clean this. I'll write it down. So same for this. We have what? We start from here. Tetraoxosulfate. What? 6 what? Acid. This one too. H3PO4. Have what? Tetraoxosulfate 5. Yeah. And by this point in time, you should not be wondering how I got this 6, how I got this 5, how I got this 5 here too. You can also locate at yourself. Get the ocean number of nitrogen, of sulfur, of phosphorus here. So that is that when you are practicing chemistry more often, you will know that this is the name of this compound. You get it's true practice that you start knowing them. Like you know, you start doing calculations and you know everything. And for instance, that all these SO4, NO3, PO4, they are literally here. They are here. Now, what formed this compound is a combination of hydrogen ion and a tetraoxophosphate 3 ion. Let me show you. Let me do that one here. So when hydrogen ion H plus combined with PO4 3 minus. This is what is the rest of this one? This is 1, this is 3. Then it's combined. This is your 3, 1, H3PO4. That was consistent. So chemistry is a very, very interesting subject. Like if you don't sabi with the understand, it's very, very interesting for you to do. Because everything in chemistry is like it's interwoven, it's interlinkable. Now this what I'm teaching you now, when you are looking at acid, base, and salt, all the knowledge you have here, it will help you a long way. That's why in chemistry, your foundation has to be grounded. And the thing is that if I started redox reactions, just like by going and start doing ionic equations, writing equations, when you are seeing all these things, you'll be wondering like, why is this? And your understanding there will not be very, very much grounded. You get, you'll not be following sidelines. So yeah. So let's look at some other compounds. I want to look at organic compounds here, I beg. That's what we're doing here. It's really take us 5